Alrighty, so we are going to look at electron configuration, and ideally you're only looking at this video once we've kind of gone through everything and, you know how it all works. So the first thing that we're going to say is there are 3 definitions that you need to know and that we apply to write our electron configurations. The first is Aufbau, and essentially it says an atom in its ground state its electrons will fill from the lowest available energy level. So this is essentially telling us the order in which our orbitals fill when we get there. The next one we have is a thing called Hund's rule. So you know me now, and I have crazy things. So in my head, Hund's begins with an S, and that helps me know what my what rule this particular one is, and it's going to go with. So Hund's rule states that if 2 or more orbitals of equal energy are available, they will fill singly before filling in pairs. Okay, and in my head, the fact that the S in Hund's goes with the singly, that's how I link them together. And the last one is Pauli exclusion principle. And in this one, my crazy is looking at the P here and the P here and linking that up. So for Pauli, no more than 2 electrons can fill an orbital. And they must have opposite spin. So it is these 2 P's in opposite spin. I link them to Pauli exclusion principle. So we use these 3 rules when we fill in our electron configurations. Now, as you know, I am a big fan of using the periodic table because you can always ask for the maths book when you are in, and you need to know how it fills. So it fills as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and finally 4p6. Now the reason S comes before D is because S is a slightly lower energy level. There are different ways of learning this. So some people like the kind of funky Christmas tree version that is 1s, 2s, 2p, 3s, 3p, 3d, 4s as far as we're concerned, followed by 4p. So to fill, we would fill 1s first, 2s first, 2p followed by 3s, 3p followed by 4s, 3d followed by 4p. Kind of makes a funky Christmas tree. But I prefer using the periodic table because that's not going to change on you. So just as a matter of interest, this here is called our S block. So this is the S block. Over here, all these guys are in the P block. and our transition metals, they get called the D block. So how you use the periodic table to answer a question is you work out the position of the thing you're interested in, and then you just use, so if you were interested in here, without even knowing what the element is, I would write my electron configuration as a 1s2, 2s2, 2p6, 3s2, and when I get to my p block, I have to count 1, 2, 2, and 3 boxes to get to where it is that I wish to go. So 3p3. Now, usually when you write your electron configurations, this is enough, but sometimes they ask you for the distribution of your electrons, and then we are applying both Hund's and Pauli exclusion principle to go with this. So there's two ways in which we can do it. We can just do our up and down arrows. So what that is saying is we're filling them singly before we fill in pairs. So this is how it would fill. S has only one orbital in there, so that's easy. But when we get to P6, they fill singly. So I have 3 orbitals in P before they fill in pairs, before they go up. So S again has only 2, but they fill 1 up, 1 down. And now for 3p3, we fill the first one down, the second one down, the third one down. So my orbitals fill singly before filling in pairs, and then they have to have opposite spin according to Pauli exclusion. There is another way. So if this was a question where it asked you to do your electron configurations, you'd get 3 marks for this and 3 marks for this if they're asking you to show your distribution of electrons. There is another way of writing it, and when you write it in this manner, you get all 6 marks in one go. So it's a slightly longer version of things, but it would look like 1s2, 2s2, and when we get to P, there are 3 orbitals and they're labelled X, Y, and Z. So this adds up to 6 as we had up here. We're followed on then by 3s2, which is fine. And now our 3p3, it'll fill singly, so we'll fill 3px1, 3py1, and 3pz1. And all of those together will get you 6 marks straight away. Now, we'll come back to electron configuration in a second, but just to say there are 3 things that you can, or pieces of information that you can get from your electron configuration. The first is asks you for an energy level, and it'll be asked as a definition, and then it'll ask you how many energy levels. So this is again something that you need to learn. So an energy level is a definite amount of energy that an electron has. The next thing that you can be asked is about sublevels. And a sublevel is a division of your main energy level, is a division of the main energy level and it is made up of 1 or more orbitals of equal energy. So our s orbital, there is only 1 of them, and our p orbital, when we get there are 3 of them, and our d orbitals, when we get there are 5 of those. Okay, so that's our sublevels. And then finally, the last one we get to is orbitals. So our orbitals are essentially, it's got a definition, it is a region in space. where the probability of finding an electron is high. Now, some candidates will, instead of writing region, they will write area. That is not a good idea because chemistry has maths in it, and area refers to 2 dimensions, whereas orbitals are found in 3 dimensions. We have said that the orbitals have certain letters that signify them, so we have an S, P, D, and an F. You have to know about the shape of your S. So it is, as we said, it's a 3-dimensional thing. So it is spherical in shape, not round. Our P is a dumbbell shape. Dumbbell, I can spell it. Possibly not, but you know what I'm talking about. And you have to be able to draw it. So it literally looks like this. So we get one, this is our X one. There would be a Y one, so it goes up and down, and the Z one goes across the page. So the electrons, when they are traveling in this, they are following the figure 8 path. And obviously if they have opposite spin, one will be going top to bottom and the other one will be going bottom to top. But they will follow the shape of the orbital. We don't have to, as I say, draw a shape for D or for F, but we do have to be aware that D has 5 orbitals in it. So we are going to start with a question or two, just to see can we figure some stuff out. So the first one we're going to do is we will write the electron configuration for magnesium. So magnesium is found in, find it up here. So this will be where magnesium is going to be up here, wrong color, is going to be here. I do have that right in my head. Nope, the next one down. Apologies. So this is the position of magnesium on my periodic table. So we know it's going to end in 3s2. So we then just start going through it. So 1s2, 2s2, 2p6, 3s2. If I'm just showing my electrons in a box, underneath it they fill singly before filling in pairs, and we finally go up and down for our S. So in terms of, you need to find out number of energy levels. The hint we've given for this is it's the biggest number. So the biggest number in this case here is 3. So there are 3 energy levels in this particular electron configuration. The next thing you have to do is number of sublevels. And we've said the hint for sublevels is you literally count your S's and your P's in your configuration. So in this case, we are looking to count 1, 2, 3, 4. So in this particular electron configuration, we have 4 sublevels. Okay, and then the last thing it's going to do is it's going to ask us to do orbitals. And this is why the electrons in a box method can be helpful to help you figure out orbitals, especially if you have something like P3, P2, P3, P4. So orbitals, we are literally dividing, knowing that S has 1 orbital. We know that P, when it's full, will be 3 orbitals. But we just have to be aware here for this is, are they half filled? So when we're doing it, this one is easy because it's 1, 2, 3, 4, 5, 6. So this, in this instance, is going to give us 6 orbitals. Now, I haven't said, but you may want to write your full electron configuration. So it would look as 1s2, 2s2, where we expand our p's, 2py2, 2pz2, and then 3s2. So as you can see here, if you're trying to figure out orbitals for this, It literally is counting 1, 2, 3, 4, 5, and 6, and that will give us this. So that's kind of why your extended one is a nicer version. Now we have two elements that light bulbs need to go on if you are being asked to write their electron configuration. And I'm just going to go up here to this, and the ones now that we are looking at in this case are chromium here and copper here. So as I say, usually you look at the position of where they are in your periodic table, and then you fill in all of your electron configurations, and it usually works. But something weird goes on with chromium and with copper. So starting with chromium, expected would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. But in this scenario here, it's more energetically favorable. So if we just look at our 4s2 when it's written like this, remember these guys fill singly, and we have an unfilled one here. It is more energetically favorable for one of the electrons from our s to come and fill this box. And now I have 5 half-filled d orbitals, and that is energetically more stable. So this is what will happen. So our electron configuration now becomes 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. So it's really, really important that you get this part right. Again, we can do our electrons in a box underneath it if we so wish. So up, down, up, down, up, down, 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 up, because they're filling in pairs, up, down, and again filling singly before filling in pairs. And obviously now we have down, 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 5. We can do your p's expanded, so we can do 3px2, 3py2, and 3pz2 here, and similarly 2px2, 2py2, and 2pz2. Now there are names for the d orbitals, but for leaving cert chemistry we don't do them, so this method becomes the better method if you have to count energy levels and orbitals and sublevels. So having a look at this just very quickly, our energy levels in this, it's the biggest whole number, so that has to be 4 is the largest. We look at our sublevels, so we've said that's counting your S and your P's and your D's. So we have over here, we will have 1, 2, 3, 4, 5, 6, 7 sublevels, and our orbitals then, this is where our electrons in our box work out. So we will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 orbitals in this particular one. So again, copper. Copper is the one that resides just next to zinc in the end of our transition metal block. And if you were to look at its position on just the periodic table and write your electron configuration from it alone, you would be getting 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. And again, this is the way the electrons look. So they fill singly, so 5 orbitals fill singly before they fill in pairs. And now it is more energetics encouraged to move at the electron from the 4s1 to here, because when that happens I now have 5 full d orbitals, and that is very stable, even more stable. So we rewrite our electron configuration as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, as habit, 4s1, 3d10. So you need to recognize this. we can do our electrons in a box underneath it. So again, fill singly before filling in pairs. We now have 1 here, and now we have 1, 2, 3, 4, 5, and these now are now full. So in terms of our energy levels, we've said it's the biggest number. So in this case, our biggest number here is 4. We then have our sub-levels. Again, that is our S's and our D's and our P's. So it is going to be 1, 2, 3, 4, 5, 6, 7 sub-levels. And then finally we get orbitals. And as I say, your electrons in a box. This is why they are good. So we are now counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 orbitals here. The last bit on this that can sometimes cause individuals issues is when we have to write electron configurations for ions. And then people get confused and can't work out what it is we should be doing. So I am going to start. I'm going to go up, I think, and I'm going to go across. So here is our periodic table. We are going to look at chlorine to begin with. So I'm looking here, that's where fluorine resides. I can do this. This is where chlorine resides. So chlorine by itself, looking at our periodic table, would write as 1s2, 2s2, 2p6, 3s2, and then we go to 3p5. So if we are looking at a chloride ion is Cl minus. How did I get this minus? So what it means, if you have a minus, you have gained an electron. So this says this has an extra electron. So now all that is going to mean is that we are going to add 1 electron on to our electron configuration of chlorine to get chloride's electron configuration. Essentially, we've now turned it into the noble gas next to it, which is going to be helium neon, is going to be argon. So 1s2, 2s2, 2p6, 3s2, we're now at 3p6, which is the exact same electron configuration as you would see for the noble gas next to it in this position here. Okay, the other one that we're going to do is something like magnesium. So we've already done our electron configuration for magnesium earlier. And just to remind us what it was. So magnesium by itself is this red here, and that is 1s2, 2s2, 2p6, 3s2. So if we were now to look at the electron configuration for a 2+ ion, what's happened is it has lost 2 electrons. So these 2 electrons at the very, very end are now going to not be present in a magnesium ion. So we now shorten it to 1s2, 2s2, 2p6, and essentially we have removed the electrons, and we now make this particular magnesium 2+ acts like neon, which has this position in our periodic table. So I hope this has been helpful. Learn your definitions and apply them. So the Aufbau, the Huns and the Pauli need to be learned so that you can apply them for yourself. Knowing these 3 definitions, very helpful because they're asked all the time, and then knowing how to use your electron configuration to get them will help you no end.